It's a pleasure to be here, and I have been enjoying the talks and especially the in-depth discussion sessions. So thank you so much again to the organizing committee and to you, Katie. So today I'd like to tell you a little bit about my research on device algorithm co-design for efficient in-memory computing using emerging non-volatile memory devices. So as many of us already experience, in the first hand, artificial intelligence based on deep neural networks has already had a huge impact in our lives. So in the last 10 years, we have observed many big steps in various applications once we thought impossible, such as language translation, computer vision, autonomous vehicles. But in addition to these well-known applications, there are numerous areas that deep neural networks have been adopted, such as medical research, disease detection, finance risk prediction, infrastructure safety, weather forecasting, and numerous other ones that I could not list in the slide. So when it comes to benchmarking these powerful algorithms against human, generally the application choice is gaming and machine intelligence. So most of you might remember Google DeepMind's AlphaGo winning over all the world champions a couple of years ago. And that actually brought a lot of excitement in the AI community. It was a great success. So if we take a closer look to this benchmarking and compare the AI against human in terms of energy efficiency, we can see that there's a huge gap in energy consumption to perform the same type of task. So for playing Go, AlphaGo requires like 2000 CPUs, 300 GPUs, which runs around like 400 to 1 megawatts of power. And that costs an electric bill per game, which is around $3,000. On the other hand, the human contestant is super energy efficient. It runs on a biological brain, which only consumes 20 watts. And it will be just fine with a Big Mac per game, which is only $3.99. Of course, this is a joke, and I'm hoping it's an appropriate joke considering my talk is after the lunchtime. But it is actually important to point out the huge gap and discrepancy in terms of energy consumption to perform a similar task between the humans and these large-scale artificial deep neural network algorithms. So energy efficiency is one of the biggest challenges of AI. These huge networks with massive amount of parameters, they quickly drain the batteries for mobile applications, so their use in the edge applications is significantly limited. And in addition to that, they substantially increase the total cost for data centers. So in addition to energy efficiency, another challenge is scalability. So every year at conferences, there are new networks that are larger and deeper. So the scaling goes on the algorithmic side, but hardware does not necessarily keep up with that. So, and that basically causes, that is one of the main causes of the increasing implementation inefficiency. And finally, speed and training time are the major drawbacks for some applications that require real-time processing, such as autonomous applications. So sometimes training these large-scale neural networks can take a time in the order of like weeks to months. I guess for the early demonstration of AlphaGo, it was around 6 months. So these challenges are extremely difficult if we only focus our efforts on the improvements in the algorithms. So, and the reason for that is the inefficiency arises as a result of the discrepancy between the von Neumann architecture and the high level of parallelism that is required by the neural network operations. So if we look at all the basic neural network operations, such as filtering, matrix qualification, weighted sum, they all require massive amount of data being shuffled back and forth between memory and processor. And memory access is the major energy bottleneck for implementation of these large-scale neural networks in the hardware. So we can better understand it by comparing the energy cost of different operations, as shown on the bottom right-hand side table. So reading data from DRAM actually consumes orders of magnitude larger data compared to other operations, such as add or multiply, or even the reading the data from on-chip SRAM memory. So this is particularly more problematic for large-scale neural networks, such as AlexNet, which require thousands of million DRAM accesses. So for these large-scale networks like AlexNet, so memory access consumes around 85% of the total energy. So although there are some architectural advances, such as hardware accelerators, application-specific integrated circuits, Expansive off-chip memory access and limited on-chip memory capacity continues to be the major limitations for efficient implementation of neural networks in the hardware. So one solution that comes to our mind, of course, to be reducing the data movement, and that can be done by performing some of these matrix operations by using the memory storage elements, which we call in-memory computing or compute in memory. So emerging non-volatile memory devices have been proposed for in-memory computing, and there's a lot of efforts in our community in utilizing interesting behaviors of these emerging non-volatile memory devices for neural network applications. Emerging non-volatile memory devices are simple two-terminal devices, which are mostly nanoscale. And because they are nanoscale and they can be integrated in 3 dimensions, so they can actually provide very high on-chip weight storage capacity. So in addition to memory in computing, they can also allow very, as a replacement to SRAM, very high density on-chip weight capacity. And the characteristics of these devices are suitable for implementing synaptic weights in the hardware, and because they can actually be programmed multi-level conductance states that I will tell more in the rest of the presentation. So these two-terminal emerging non-volatile memory devices, they can be integrated in crossbar architectures. And crossbar architectures, as you might have heard in the previous talks, are particularly suitable for implementation of or mapping matrix operations onto the hardware. So if you envision a neural network layer where you have the inputs and the weights, so we can directly map this operation, weighted sum operation, onto this crossbar array by converting the inputs to the voltage values that are applied to the word lines of the crossbar. And if we read the current from the vertical bit lines, that would give us the total weighted sum, because that will be basically a summation of the voltages multiplied by the conductances of the synapses or these emerging non-volatile memory devices. So similarly, this crossbar architecture can be used to accelerate some other matrix operations, such as other matrix multiplication, convolution, and MEC operations as well. So in addition to that, the conductance or the resistance state of these devices can be modulated on the go. So they also offer a suitable platform for implementation of online learning and classification. So in-memory computing with using this nano memory devices basically target 2 applications. So the first one is offline classification. So, and that is probably the most imminent and straightforward first application that would be eventually commercialized. So in offline classification, training of the neural network is performed in the cloud, and that is done by using high precision. Like we can use 64 to 32-bit precision, weights and activation functions, and achieve very high accuracy. Once the training is completed, the weights are quantized, and then they are programmed onto the crossbar memory array for performing inference offline. And in this case, we perform programming only once, and if the weights need to be updated, so the training that needs to be done through the communication with the cloud. So that is offline classification. The other one, which is much more challenging, is online learning, which requires use of quantized weights to update the weights in the hardware during the training. So for online learning, it's very important to develop devices which can provide high enough resolution, high enough precision, so that we can perform online learning with high enough accuracy. So for both approaches, for both applications, in-memory computing using emerging non-volatile memory devices potentially offers an area and energy efficient approach for implementation of different neural network algorithms in the hardware. So what type of emerging non-volatile memory devices we have? So if you look at the literature, there are many, tens or maybe hundreds of different types of Synapse candidates have been published. In this slide, I just included 5 of them, which are mainly from the memory community, memory literature. But in addition to the ones that I'm gonna show and I'll discuss today, there are many other different types of memristors, organic devices that have been focusing on different applications of neural networks, mainly representation of weights in the hardware. So in this slide, I have 5 memory examples. The first one is STT-MRAM, spin torque transfer magnetic access memory, which uses programming of the magnetic state of the free layer by applying electrical currents. So the second one is phase change memory, and phase change memory uses a different mechanism. So by applying electrical pulses between two electrodes, we can actually program the phase of the material to store the weights. Resistive and CBRAM memories are different types of emerging non-volatile memories. They are similar, but they both utilize filamentary switching. So to program the device into different conductance states, we form a filament between the top and bottom electrodes. And the last one is FERAM, which has attracted a lot of attention in the recent years, ferroelectric random access memory, which uses state of the ferroelectric layer to store information. So in my group, I work with 4 of these devices: STT, MRAM, PCM, RAM, and CBRAM. In addition to developing individual devices, engineering their device characteristics to make them suitable for implementation of weights in the hardware, we also closely collaborate with our industrial partners to assess and benchmark their capability of the large-scale arrays for implementation of various operations related to neural networks. It's also important to point out that I keep using the word emerging, but some of these technologies have already been demonstrated in the industrial scale. Qualcomm demonstrated 1 gigabit embedded STT-MRAM memory embedded within their processors. And also Intel crosspoint memory is supposedly based on a phase change material, and it is 3D, so it stacks 2 layers of phase change memory. And other companies such as Adesto and TSMC have demonstrated large-scale resistive or CBRAM memory devices for mainly for digital memory applications. So these devices, emerging non-volatile memory devices, can be programmed into multi-level conductance states, and the programming scheme depends on the switching characteristics of the device. It could be either using identical pulses, which is the simplest scheme, or it may require pulse width or pulse amplitude modulation. So all of these characteristics they depend on the switching method of the material and the device itself. So my background is in semiconductor devices, and as device engineers, we always ask the question, so what is the ideal device? So I have shown you 5 different examples. So which one is most ideal for implementation of weights, neural network weights in the hardware? So that type of question would be straightforward for CMOS or digital memory applications, where we had the guidelines by Moore's scaling law, which was governing the semiconductor technology for more than 3 decades. However, answering that question is a lot more difficult for neural network applications. So if you look at the neural network applications, so we can try to understand it by looking at the device level metrics and system level metrics. So on the left, I list the device level metrics that can be measured and compared within each other to decide which technology would be optimal or best candidate for neural network applications. So that includes device dimensions, density, energy consumption, programming time, number of states, dynamic range, retention, and endurance. And on the right, I basically list the system level performance metrics. And these system level performance metrics, although all of them are very important, they could basically, their relative importance can depend on the specific task, data set, or the complexity of the application. For example, if you look at the throughput could be very important for real-time applications. So if you look at energy efficiency, it's definitely critical for embedded mobile applications. And the latency is probably the most important parameter for applications that require like interactive autonomous applications. So if you look at, so this system level performance needs basically are very important. Their relative importance depend on the application. But we should always keep in mind that depending on the targets, so they should be the guiding principles, but we should follow a top-down approach where we can actually focus on system level performance metrics and try to engineer the relevant device level metrics according to achieve our target performance. But if you look at the relationship between the system level performance metrics and device level performance metrics, for instance, accuracy depends on device density, number of states, dynamic range, retention, and endurance. Similarly, throughput, energy efficiency, they all depend on multiple of these different metrics. So the relationship between the device level metrics and system level performance metrics, basically, it forms a neural network itself. And that basically shows that it's very difficult to come up with a single precise list of device level metrics which will work for all sorts of neural network applications. So devices really need to be engineered by using a top-down approach in opposition to what we are used to from CMOS, which is following a bottom-up approach. At the top of that, we also face with several other challenges when we attempt to map the neural network weights or operations onto these emerging non-volatile memory arrays. So first of all, we know that the neural network algorithms are designed for software implementation. So it's not always possible to directly map them onto the characteristics of our emerging non-volatile memory devices. In addition to that, these devices also exhibit a lot of different types of non-idealities. And here I listed 3 of them. One is basically limited number of conductance levels. And in some of these devices, they can also exhibit very abrupt conductance change, which may result in loss of information. So the devices can exhibit device-to-device or cycle-to-cycle variation when you program them on the go for online learning. Or another non-ideality is resistance or conductance drift. So if you program these devices over time, you may lose data because the resistance state of the device changes in either way. So this mismatch between the software and hardware and also the device non-idealities can significantly impact the accuracy. And if you try to basically compensate for those by using some peripheral circuits or making your algorithm more complex, that can significantly increase energy consumption, complexity of the system, and the cost. So the solution to that is to follow a top-down co-design approach, which is guided by the system-level performance metrics, depending on what are the specific needs of your application, and then tuning both the technology, the devices themselves, and the algorithms to optimize the performance. And today, I like to show you 3 examples from my group on device algorithm co-design. So I mentioned that these emerging non-volatile memory devices can be used to represent the weights in the hardware, but we know that most of these devices, they exhibit limited number of conductance levels. So we are interested in developing adaptive quantization techniques to perform online learning and training by using low precision devices with small number of conductance states. So in the first part, I will discuss our work on adaptive quantization. Then I will move over to using a device algorithm co-design approach to minimize the energy consumption, both in the device level, and present some algorithmic approaches that can be adopted to spiking neural networks to reduce the energy consumption during training. And finally, I like to introduce you a new device which exploits inherent nonlinear behavior of some nanomaterials for implementation of activation functions on the hardware for stacking and scalability of neural network models in the hardware. So let's start with the first part. So if we consider emerging non-volatile memory devices, we can use them for representing weights in the hardware by programming them to multi-level conductance states. And most of these devices, as I mentioned, they exhibit limited precision. So they exhibit only limited number of conductance states. So this limited precision can be a very critical factor that can decrease the accuracy, particularly for online learning and some of the offline classification applications. So the effect of limited precision have been studied by many groups in the literature. You can see the results on the right-hand side. So it's particularly detrimental for online learning. And the general conclusion from the community is that to perform high accuracy, to have high accuracy, it's important to have a bit precision of at least 6 to 7 bits for implementation of online learning. So there are many different types of synaptic devices that we are interested in, but first I like to introduce the phase change memory-based synaptic device. On the left-hand side, you see a cross-section transmission electron microscopy image of our phase change device. So this is a very simple 2-terminal device with a metal electrode and deposited phase change material at the top. So the working principle of this device is as we flow the current across this nanoscale heater electrode, so we can actually induce local heating to the phase change material and change the phase of the material between amorphous and polycrystalline. So in the amorphous state, the material exhibits high resistivity, and in the polycrystalline state, it exhibits low resistivity. And by programming the phase of the material between amorphous and polycrystalline, we can store the information in the phase or the resistivity of the device. So because the resistivity or the conductance of the device is basically controlled by the amorphous volume, we can actually increase or decrease this amorphous volume with the application of electrical pulses. And on the right, we can see that we can actually modulate the conductance 2 orders of magnitude by application of pulses. In that case, it's 150 pulses applied across this phase change synaptic device. So this consecutive application of pulses, this very gradual resistance, conductance increase and decrease is repeatable over many cycles. The device shows great endurance, and it can also be used in different resistance regimes. So it could be either programmed to multi-level states in the high conductance regime or the low conductance regime. So for applications that require really minimal energy consumption, perhaps low conductance regime would be more desirable because the current levels are much lower, so the energy consumption would be less. But if we zoom in the switching characteristics of the device, in that regime, low conductance regime, we can see that it's nice and linear, it's very gradual, but in some range of conductance, it exhibits some abruptness, which is a non-ideality specific to this phase change synaptic device. So we develop different types of devices, and we always use this general framework that I'm going to be explaining in this slide. So we extensively characterize the conductance response of the devices, and then also the non-ideal effects by measuring many devices and looking into statistical distributions. And then these device characteristics are used to develop physics-based accurate models of the devices, which are both used for implementation of weight updates in the neural network models. So in that case, for the weight update, we sometimes use directly the experimentally measured values and the weights onto those values to perform weight updates with the realistic device data. But we also use the device models to fine-tune the weight update characteristics to optimize the classification accuracy. And that basically provides a feedback to us to further engineer our device towards the desired characteristics, which minimal amount of non-ideal effects and the desired conductance response. So we also work with various different types of neural network models, including artificial neural networks and spiking neural networks. Today, I like to give you an example with a very simple spiking neural network model that we use for implementation of unsupervised learning in the hardware. So the choice of this simple spiking neural network model is because our final goal was to implement it on the hardware completely. So because it's only 2 layers and 1 layer of synapses is connecting the input neurons and output neurons, we can directly map this model onto the crossbar arrays. And for training our spiking neural network, we used MNIST dataset. So the MNIST digits, they are converted into poson spike trains. We converted the pixel intensity into firing rate. It's a linear mapping between the pixel intensity and the input firing rate. And then during the training, we basically monitor the membrane potential of the output neurons that are simply calculated by weighted sum. So as the input digits from the MNIST are presented to the input layer neurons, we basically look at the membrane potential of the output neurons, and the firing probability of the output neurons is determined by a softmax distribution. So the training method is also very simple because we really want to fully implement it in the hardware. So we did not want to go something much more complex, such as an artificial neural network or use of back propagation. So in this case, the method we use is very similar to the spike timing dependent plasticity rule that is developed by Wolfgang Maas. Here we look at the spiking activity of input layer neurons and the output layer neurons. If their spikes, they overlap within a time window of 10 milliseconds, the synaptic weight is increased based on the weight update rule. And then if they do not overlap, if the spiking activity is outside of this 10 millisecond window, the synaptic weight is decreased accordingly. So the training is completely unsupervised, and at the end of the training, we represent the whole MNIST data set one more time to assign the labels to the output neurons. So to implement the neural networks in the hardware, we really need quantization to reduce the bit precision and to perform neural network calculations. So the conventional method for quantizing weights onto the discrete conductance values of these emerging non-volatile memory devices is uniform quantization, which basically maps the continuous neural network weights into discrete device conductance linearly. So uniform conductance is rather simple and it's widely used, but it is important to emphasize that if you intend to use it for implementation of online learning or training in the hardware, uniform quantization treats all the weights with equal importance. And it also ignores the initial distribution of the weight evolution during the training. And as a result, for most of the records that are utilizing uniform quantization, implementation of training in the hardware results very low accuracy. So a solution to that could be adaptive quantization, which maps the device conductance levels to the weight values based on their distribution during the training. So in order to perform adaptive quantization, we utilize the evolution of the weights in the first 5,000 training samples from the MNIST dataset to train an adaptive quantizer, basically to obtain the quantization intervals and their corresponding quantization value for mapping the weights. And depending on the device characteristics, so the weights could be distributed in different ranges, such as we can have more quantized levels for the medium weights, low weights, or the high weights. So at the bottom, we look at the weight distribution of the output neurons when we perform training by using a 4-bit adaptive quantizer on the right and ideal 64-bit floating point. So these images, they basically show the weight distribution of the output neurons because it's only two-layer neural network. If you look at the weights between the output neurons and input neurons, they directly show the MNIST digits, which is a great way of probing the learning process itself on the go. So if you look at the 64-bit case, we can see that all the output neurons, they very precisely learn the MNIST digits. But if you look at on the right-hand side, the 4-bit adaptive quantizer, although it's a little bit more noisy, it can still basically learn the MNIST digits successfully. So that was basically very interesting. So here we further investigated the performance of adaptive quantizer for different bit precision. And on the left, I show just an example of how our adaptive quantization scheme distributes the quantized levels to the device characteristics for 5-bit precision. And on the right, we see the accuracy results for online learning using our spiking neural network model as a function of bit precision. So the purple line basically shows the uniform quantization, which obviously shows a very steep decrease as the bit precision decreases to 5 to 4-bit precision. But when we use adaptive quantization, we can see that the accuracy can be significantly boosted for 5-bit and 4-bit precision. So adaptive quantization also achieves comparable accuracy to floating points for precisions which are larger than 6 bits. In addition to improving the accuracy for low bit precision, adaptive quantizer also helps to mitigate the effect of the abruptness and the non-linearity in the device conductance characteristics that would effectively reduce the accuracy. So it's a way that we can fine-tune both the algorithm and also by keeping in mind the non-idealities of the devices. So that is just an example of device algorithm co-design and how we need to fine-tune quantization or any other algorithmic approach by considering the specific algorithm, in that case SNN, and also the device characteristics. So now I'd like to move to the second part and tell you a little bit about our device algorithm co-design approach for reducing energy consumption. So energy consumption is a big challenge, as I try to overemphasize in the introduction slides. So the first emerging non-volatile memory candidate I worked with was phase change memory. And I love phase change memory because it's very uniform, you can have many levels, and it exhibits very low variation from cycle to cycle. However, when it comes to energy consumption, because you need to melt and change the phase of the material, the energy consumption is a little high compared to other candidates. So we were interested in looking into other memory devices which can exhibit extremely low energy consumption. So in collaboration with our industrial partner, Adesso Technologies, we developed subquantum CBRAM devices for implementation of weights in the hardware. So this is a conventional filamentary CBRAM device where you form a conducting filament between the active top electrode and bottom electrode. But the novelty here is that the filament itself is not made of metal, as it is the case for conventional CBRAM devices. If the filament is made of metal, there will be a lot of current flowing during the programming and read operation, and that would significantly increase the low conductance, will significantly increase the energy consumption for CBRAM. So the idea here is to replace this metallic filament with a semi-metal or a semiconductor so that you can reduce the conductance in order to reduce the device level energy consumption. And by replacing this filament with tellurium, we demonstrated that energy consumption per programming can be reduced to 100 femtojoules for subquantum CBRAM devices. Similar to phase change memories, subquantum CBRAM devices can also be programmed into multi-level conductance states. So at the top, you see the switching characteristics when we program them by using consecutive pulses. And in addition to use of consecutive pulses, subquantum CBRAM devices can also be directly programmed to desired conductance levels from the low conductance state. And that is enabled by the architecture that these devices are integrated, which is one transistor, one resistor array, in which each CBRAM device has a selector transistor, which enables us to access it and also control the current that flows across the CBRAM to directly program it into the desired conductance level. So now I like to also introduce an approach that we adapted, a bio-inspired approach that we adapted from deep neural network literature. So it's synaptic pruning. So it has been suggested that in the brain, synaptic pruning eliminates the inefficient synapses during the developmental stages. So this schematic shows the synaptic density at birth. It significantly increases around 6-year-old or 7-year-old, and then decreases back again as the brain gets more and more mature. So this synaptic pruning inspired the deep neural net literature, and it has been adopted to reduce the number of network parameters. And in DNN literature, it has been demonstrated that it can significantly reduce the energy consumption by compressing the network. So for AI, for the artificial neural networks, the pruning is generally applied after the training. But in the brain, it's kind of on the go. As the brain gets more trained and developed, it also prunes at the same time. So it gave us an inspiration that can we actually utilize a similar mechanism to reduce the energy consumption during the training when we implement spiking neural networks in the hardware. So we investigated pruning during the training for spiking neural networks. So in our method, so we looked at the spiking activity of the output neurons to decide when the neuron can be pruned. And when we pruned the neuron, we actually looked at the synaptic weights between the output neurons and the input neurons. So we explored two methods, pruning and soft pruning. Pruning is very similar to conventional pruning in deep neural networks. When the weights between the input and output layer are pruned, the low weights are directly set into 0. And the other method is we call soft pruning. In the soft pruning case, we prune the weights during the training, which means if the weights are pruned, they are either kept in their current values or they are programmed to a constant value, and they're not updated in the rest of the training. So we can still save energy by not updating those weights. But if it is necessary, they can be recalled at the inference stage in their constantly programmed values. So at the bottom, we see two movies that are showing weight visualization during the training when we have no pruning and soft pruning on the right-hand side. So when an output neuron reaches to a maturity level to recognize a certain digit, our pruning algorithm basically prunes the synaptic weights that are below a certain threshold synaptic weight value. And pruning percentages can be decided by the user in the algorithm. So in this case, our soft pruning method basically looks at the low weight values and mainly removes the weights that are learning the background pixels of the MNIST data set. On the right, we have the accuracy results as a function of pruning percentage. we demonstrated that our pruning during the training method can be successfully applied, can still provide high enough accuracy, and we can prune 70 to 80% of the network to reduce the energy consumption. So for hardware implementation of our spiking neural network algorithm, we have two options, analog versus digital. So for the digital case, because we need to represent the weights with a certain quantization and precision, so we need to group n binary devices to represent one single weight. So it depends on the desired precision. If it is 6 bits, six devices are grouped to form one synaptic weight. And as a result, digital approach potentially basically occupies much larger area compared to analog approach. On the other hand, we know that the digital approach has the advantage of already existing infrastructure, including peripheral circuits. So we can utilize existing memory chips to directly implement training in the digital synaptic cores. And in addition to that digital approach, because it's using binary weights, so it is less prone to variations and noise. So on the other hand, the analog approach, which we use synaptic weights that are basically representing multi-level conductance levels, can potentially offer much smaller area and better energy efficiency. But the analog synaptic weights, they are more prone to cycle variation, and the number of weights that we can implement is limited by the noise level. So there are also some limitations. So both approaches could be advantages depending on the application. So the trade-off between analog and digital strictly depends on the type of application that you're interested in. For instance, if it is only offline classification, perhaps digital approach is sufficient. But in addition to that, it's very important to evaluate both architectures by directly using the device characteristics, because depending on the device characteristics for the digital versus analog application can significantly change the efficiency outcome. So we also developed methods for implementation of pruning in the hardware. So there are two methods that we can map pruning onto a hardware implementation. So the first one is mainly for targeting the digital application. In that case, we can actually use an extra binary device, increasing bit precision by 1, to basically serve as a flagging mechanism in the hardware to indicate if a synaptic weight is pruned or not. So in that case, we can actually read that bit and decide to further train or not train that. So by using circuit simulators, we also investigated the energy and latency overhead of adding this additional bit as a flag for pruning, and observed that the energy consumption and latency does not significantly increase by adding that additional bit, but area will of course slightly increase due to that extra binary device. Second approach is basically probably an easier one if the device characteristics allows. So in that approach, we can actually prune the cell by resetting its conductance to a very low value, which cannot be recovered by using standard voltage or current pulses that we use for programming. So recovering that would require some additional reset current, which may be like a longer duration or higher amplitude. But during the training, we can actually reset it to a very low conductance value to permanently program it to that low state. Here in this table, I like to compare the performance metrics in the system level for hardware implementation of spiking neural networks using our SNN algorithm. So we did these simulations using NeurSim platform. So NeurSim platform is a circuit macro model that is developed by a colleague of mine in Georgia Tech, Shimen Yusguru. So NeurSim platform is conventionally used for multi-layer perceptron or some of the convolutional neural net models. So we developed the spiking neural network module for the NeurSim to simulate energy, latency, and area for digital and analog implementations of our SNN algorithm for unsupervised learning. So here, if you look at the performance results, we can see that for our algorithm and for our device characteristics, so digital approach offers better accuracy, shorter latency, and lower energy consumption. But on the other hand, analog has the advantage of smaller chip area. So it's important to emphasize that, so these are not generalized results. These are for the simple SNN algorithm we use, and for the specific device characteristics, CBRAM devices, that we developed. So it's important to keep in mind that it requires careful characterization and simulation of performance for every new technology. So after seeing that digital performs significantly better, we decided to proceed with a digital demonstration by using a large-scale subquantum CBRAM chip in collaboration with the Adesto Technologies. So this 512 kilobit subquantum CBRAM chip is used to implement learning and pruning in the hardware based on our SNN algorithm. On the right, you can see the experimentally obtained bitmap before the training, during the training, and after the training. So the blue pixels, they show the prune weights. And for this training, we used 8-bit precision. So we mapped neural network weights to 8-bit precision. And for this case, we used linear quantum. And our hardware demonstration have shown reasonable accuracy, very close to theoretical accuracy predicted for our SNN algorithm. And we demonstrated that pruning during the training can significantly reduce the number of device updates and energy consumption. So that is a method that can be further improved and generalized for other applications. So now I'd like to switch gears and tell you a little bit about a new device for implementation of activation functions in the hardware. So as all of us know, like deep neural networks, artificial neural networks, they consist of many layers, sometimes hundreds layers. And the neuron layers are basically connected by synaptic weights. So if we take one of these layers, hidden layers, and zoom in and take a look at that, so the operations in the simplest form is that the inputs are basically that are coming into the layer are multiplied by the weights, and the multiplication results are accumulated in the neurons. And the output of a neuron, which needs to be fed into the next layer, is basically calculated by passing the weighted sum through a nonlinear activation function. So the neuron has two functionalities. One is weighted sum and the other is the activation function. So if you look at the neuromorphic devices literature, so mainly we have been focusing on implementation of weighted sum by using this crossbar arrays. And demonstrate in the hardware that by using the analog approach, weighted sum can be successfully performed. But if we are interested in a realistic application, it's not only a single synaptic core, it's not only a single synaptic layer. So we really need to map, stack multiple synaptic layers and perform the activation functions in between them to generate the outputs of each layer. So traditionally, the activation function calculations are implemented in 3 different ways. So the most common one in our community, in neuromorphic devices community, is perform the multiply and accumulate operations in the crossbar array, but then use an external general processor to calculate the activations. So that actually contradicts our initial goal of reducing the data movement between memory and processor, because now instead of moving the weights, now we need to move the activations in and out of the memory. And for large-scale neural nets, which have a huge amount of activation function, number of activations, that movement of activation can dominate the energy consumption. So there are 2 other approaches: is either to use an analog amplifier based on op-amps to implement large and complex neuron peripherals, or use analog to digital converters for implementation of activation functions. So if you look at the analog to digital converter example, the computation of one activation function using ADC consumes an energy which is comparable to the total energy consumed by the synaptic array for performing 1 meg operation. So it's very area inefficient and costs a lot of energy. So what could be a potential solution? So we are interested in developing new devices which can implement nonlinear activation functions that are required to stack multiple neural network layers in the hardware. So the input to these activation functions should be the weighted sum that are coming from the crossbar arrays, and then the output should be a voltage that could be applied to the next crossbar array on the line. So there are various types of activation functions in the NN literature. So the simplest one is a step function. And in addition to that, there are various other activation functions such as sigmoid, hyperpoling tangent, rectified linear unit that have shown to be performed better in terms of accuracy in deep neural network models. So among those, rectified linear unit is perhaps the most commonly used one. So we were interested in investigating if we can actually design a device to emulate the ReLU behavior. So if you look at the ReLU function carefully, the output of the ReLU function is linear after this transition point for the positive weighted sum values. And if the weighted sum is negative, it's 0. And it's important to remember that, so the output of the ReLU activation function only depends on the current input. So the current input is the weighted sum current for the crossbar array, and it should not have any memory. It should be, the output should be regardless of the previous inputs or the resistance states, which means the device itself should be volatile. So it should not represent any non-volatile characteristics. So therefore, the devices that I presented today, like the memristors or non-volatile memory devices, are not suitable for implementation of activation function. And it should also show very linear and gradual switching characteristics, which are not conventional for the standard devices such as diodes. So on the right-hand side, so I like to explain the activation, ReLU activation device that we developed. It's a 4-terminal nanoscale device, which utilizes a heater electrode, which is connected to the vertical columns of the crossbar array. So the weighted sum current that is generated as a result of MAC operations is that flows through a heater electrode. And the heat generated by this heater electrode basically induces a volatile resistance change in a Mott insulator device. So in that configuration, the heater is basically passivated by using an oxide layer from our nanoscale Mott insulator, which is around like 50 nanometers in size. So when the weighted sum current increases, the resistance of the Mott device decreases. And if it is used in a voltage divisor configuration, we can clearly see that the output characteristics will basically increase as the Mott resistance decreases, nicely emulating the ReLU behavior for the implementation of activation. So the only remaining part is basically demonstrating that it is gradual and also volatile. So conventionally, Mott insulators, they exhibit very abrupt switching as a result of thermal electrical switching mechanism. So we engineered the device structure of our 4-terminal device to exploit the thermal-driven domain-wise switching rather than electrical filamentary switching, which results in abrupt transition. For our case, the metal insulator transition is driven by temperature, but only the small domains in the material whose critical temperature is below the device temperature will transition into the metallic phase. Because these domains have a lot of different, they show some variation in size and critical transition temperature, we can actually very gradually control the switching characteristics of the Mott insulator when we use our device configuration. On the right-hand side, you can see that resistor basically very linearly and gradually reduces as a function of heater currents. And when we use it in the voltage divider configuration, our device nicely implements ReLU activation function in the hardware. So the x-axis is the heater current and y-axis is the output of the Mott ReLU device. And on the left-hand side, we can see that the device is completely non-volatile. So the resistance of the device switches only when the heater current is applied. So otherwise it goes back to original low conductance state. And the device shows very minimal cycle-to-cycle variation, which is quite interesting and nice compared to the high level of variation we use in metal oxide-based RAM devices. So the latency of the device is around like 60 nanoseconds, but we investigated that part of it is due to the parasitic capacitances as a result of the insulator oxide between the metal lines. So that can be further reduced to sub 10 nanoseconds by optimizing the device. So if we look at the energy consumption of the Mott ReLU is around 200 picojoules. But if you look at the power components, we can clearly see that most of the total power is basically dominated by the heater. And the Mott insulator only consumes a small percentage of the total power. That tells us that the thermal design of the device, the thermal coupling between the heater and the Mott insulator should be really further engineered to minimize the energy loss due to extensive heating. And the device endurance characteristics are quite nice, so you can switch it at many cycles. So here in this bottom table, I compare the device level characteristics of our Mott ReLU to a CMOS op-amp implementation and ADC. So the key advantage of Mott ReLU is, of course, in area, because it's a nanoscale device. So we can actually we can have orders of magnitude decrease in the total area for hardware implementation. So the first thing we investigated is what would be the accuracy if we change the activation functions in conventional neural network models with the activation function characteristics of our device. So in the network simulations for multi-layer perceptron and convolutional neural nets, LeNet5, so we replaced the activation functions on the neuron layers by using the experimental Mott ReLU results that we measured directly from our devices. So we demonstrated that the Mott ReLU basically provides high enough accuracy. It's close to the ideal software simulations, which is shown by the blue line for online learning. So the small difference between the ideal accuracy and Mott ReLU is as a result of quantization, because our device shows 5 to 6 bit precision, and mainly the degradation is as a result of the quantization of the activation functions. So we investigated accuracy degradation due to variations and found that cycle to cycle and device to device variation is not very impactful unless they are more than 50%. So in the last slide, I like to compare the system level performance. To compare system level performance, we used Neurosim again. So we developed the circuit modules for our Mott ReLU activation function. And we also developed a CMOS amplifier module based on a published reference. And we also implemented the ADC activation function in the Neurosim. So on the right-hand side plot, so we are comparing the performance of LeNet5 for energy and area for these 3 different synaptic cores that are using ADC, CMOS amplifier, and the Mott ReLU activation function. So the red star is our experimental results, and the black square is the Mott ReLU when we optimize the energy consumption and the latency characteristics. So as you can see, so the CMOS one, because we have the model in the Neurosim, so we can actually study the scaling as a function of technology nodes. So that is plotted as a function of technology nodes at the top. So as you can see, the Mott ReLU basically can offer orders of magnitude reduction in energy and also area in comparison to CMOS, analog CMOS implementation and digital ADC implementation for representing activation functions, implementing activation functions in the hardware. Okay, so I like to conclude my talk by emphasizing the importance of algorithm device co-design approach. So as a device engineer, we are really interested in coming up with new ways of implementing neural network operations in the hardware. So we engineer new devices, develop models for those. But it's very important to follow a top-down design approach where we both fine-tune the algorithms and also the device parameters to basically reach the optimal performance. Pruning and quantization are critical for hardware implementation because we have to quantize the weights and we have to reduce the network sizes. As it is, some of the large-scale neural network algorithms are beyond the capacities of currently available memory arrays. So they are definitely, there is a lot of room to improve those characteristics towards hardware implementation. And before demonstration in the hardware, a critical step is performing realistic circuit simulations to understand system level performance metrics and provide feedback to upper levels, the device algorithms and pruning and quantization to further fine tune it. And hardware demonstration could basically depend on the target application. It could either target offline classification or online learning, but for both cases, it's very important to follow this systematic approach to achieve efficient implementation of neural networks in the hardware. Thank you so much for the listening. I think I took a lot of time. I like to acknowledge my students. They do all the work, and my funding agencies, my collaborators. And I like to mention that I am always looking for postdocs and PhD students. If there are any in the audience interested in, please send me an email and I would be more than happy to consider. Okay, that's
Great. Thank you so much. That was awesome. We already have a question in the chat. Stephen, I don't know if you would like to ask the question or I can read it. Okay, so the volatility slide showed 2 milliseconds between activations. How fast can you move from some to some? Also, isn't there an area heating issue that could interfere with accurate use of the Mott ReLU?
So the volatility slide showed yeah, I mean, that 2 milliseconds was just a choice for pulse implementation during the measurements. So the latency of the device is 60 nanoseconds. So that is basically the minimum that we can implement in the hardware with the current design. But this is a 4-terminal device and it's a little more complex than conventional 2-terminal memory devices. So there are some parasitic issues that needs to be addressed. I think that potentially it's possible to operate it in sub 10 nanoseconds. The switching latency of the device can be reduced to sub 10 nanoseconds. But it is something to be demonstrated experimentally. And the other question was, there was one more question.
Yeah, is there an area heating issue that could interfere with accurate use of the Mott ReLU?
So the area heating issue is a great comment. So it's a similar problem to phase change memory, because in phase change memory, we are also heating the phase change material and then basically trying to, we heat the phase change material without causing any crosstalk between devices next to each other. So that can be one factor that would limit scalability. But for phase change memory, it has been already demonstrated that it can be built like sub 32 nanometers. So I would guess that the size of the Mott ReLU, even if we reach to that 30 nanometer dimensions, could be many orders of magnitude smaller to any alternative, which we would do with the circuits. So the heating also can be reduced by optimizing the thermal coupling between the device and the heater. So in current form, we have a very thick oxide and we need to flow a lot of current and heat it a lot to be able to induce enough temperature change in the Mott insulator. But I think we can significantly reduce it, and the problem would be like very similar to what we face in the phase change memory. And I think there are solutions to that.
Thank you. Excellent talk.
Miriam has her hand up. Miriam, do you want to go ahead and ask your question?
Sure. Thank you very much. I learned a lot from this talk. I appreciate it. So my question is on that. I thought the main reason and incentive to go towards CBRAM subquantum memories was the energy issues with phase change material. Am I correct?
I mean, that was the way I presented it, motivation, yes.
So I want to know that, do you think that we should put aside phase change material, 2D or 3D? Because from my point of view, I'm not a device person, so I'm looking at it from the overall perspective. So I see different devices, different materials, all the way from a spintronic to ferroelectric to phase change, transistor, phase change 2D, or for example, a subquantum. And I know that each one of them have their own benefits. But if I want to look at it from the overall perspective, do you think that one of them is the way to go, or you want to have them all together and take advantage of each one separately?
So you should definitely not put it aside. So because among those memory technologies, phase change is one of the most mature ones. And compared to any resistive, like compared to CBRAM, its endurance characteristics are 5 orders of magnitude better. So depending on the application, let's say that you're interested in only offline classification and you need to program your devices once and maybe like a couple times if you need to update your neural network in the cloud. So in that case, so endurance is not a very important parameter for you. So you can go with the RAM memory, and especially if you are CBRAM memory, and if you are also interested in a mobile application where you really care about the power efficiency, so that would be the right choice. But on the other hand, phase change memory is very mature. It has been demonstrated in very, very large scale. It can be stackable in 3 dimensions. There are already commercially available products. So that is basically ideal for applications that require high endurance, but you are not limited by the energy budgets. So that was the overall message that I wanted to give throughout this whole presentation, is that the choice of material or the choice of device depends on your application and what you want to do with it. So CBRAM probably will not be a great one if you want to implement online learning in the hardware for a very large scale neural network. If the neural network is simple, that's fine if you do not need huge amount of parameter updates. But if it is a large scale neural network, then maybe the endurance characteristics will not be sufficient for that purpose.
Awesome. And I
did
saw
that answer your question?
Yeah, definitely. And I saw that you also have some frameworks in your lab looking at different devices and also circuit level altogether. So do you feel that there is a route to go for benchmarking these types of neural hardware? I think it will be really beneficial because it's not only, so I myself, I'm from Professor Kaushik Roy's group at Purdue, and also I work with Katie Schumann. I see a lot of different groups in different universities working in different neural hardware or, devices, but I would like to see all them together. And it's really difficult to see the connection between different groups because you see the connection is there, but at the end, as somebody out of this domain, if I want to use a specific, for example, hardware for my problem, I need to go digging out which one it's better to use. It will be awesome if we can put everything together.
Yeah, I think the large scale programs that are initiated by different government agencies are basically the purpose of those is that. So bringing in people from different areas, such as me, like people like me at the bottom, right? The device level people and people on the architecture or algorithm level, they really need to come together to develop platforms for accurate benchmarking. There are already some existing efforts like NeuroSim that we use that was developed by Georgia Tech Group is great in terms of comparing the performance of at least the different memory candidates for synaptic core implementation. But definitely it's a small step, so it could definitely need to be, we should put more efforts to increase the interactions through these large programs where people from like algorithms to devices to architectures, they work closely to benchmark the performance. So it's even very difficult in the algorithm world, right? So comparing things to each other. So life is very difficult, especially for me, like I'm a device person. It was very easy when I was developing the next generation transistor during my PhD because the metrics were so clear. We just want to increase the mobility from this to this. But now the performance needs are different and it depends on application. And each architecture is tending to be more application specific. And the critical characteristics of these devices will also depend on that. So unfortunately, there is no easy answer. And I think a lot of people in the field are also getting frustrated about it, but we have to work
Long way to go. Thank you.
This would be our point to say we are having a benchmarking and metrics special session on Thursday. So if you'd like to talk more about that, please join us there. So we're running out of time, but I have, there's a couple of questions in the chat. So from Alex, he noticed on one plot that showed the experimental device when directly compared to the ReLU had several jumps in its output value. Is the reason behind those jumps known?
Yes, so the domains. So the device is nanoscale and domains are nanoscale. When domain switch, it jumps. Another domain switch, it jumps. So it's gradual, but there are small jumps. So in the paper that is still under review, so we studied that effect of the jumps to accuracy. So luckily it's not very significant. But I mean, the device can be engineered to prevent that if it is a problem. It's just related to the domain size and the size of the domain with respect to the device. Yeah, but it's a great point. It is something that also attracted reviewers' attention. So.
And one last question, are there any simulators to realize the NVM devices that model the behavior like Verilog A or any others?
So we use NeuroSim, so it's available. So it's developed by Georgia Tech Schumann Youth Group. I think they have a model, the version that works with CNN on GitHub. So if you search for NeuroSim Georgia Tech, so it should pop up. So that is, I mean, that is the one, as far as I know, the only one that you can basically directly use the device characteristics, upload your device data, and then look at the performance, for instance, for CNN, if you use a crossbar array of your device for Mac operations. But it is not doing everything, it's not the full hardware, it's only looking at the crossbar array and its peripheral circuits, so for implementation of Mac operations.
Okay, great. All right, so I'm going to keep the other questions for the breakout room or just in the main session as we continue on. So thank you again for your keynote. That was amazing.